Hello dear students. In this video, I'm going to discuss question number 21 to question number 25 of the chapter on fluid mechanics in our book Gupta and Gupta. Alright, so the question number 21 says that the center of buoyancy always coincides with the center of gravity or coincides with the centroid of the volume of fluid displaced, remains above the center of gravity or remains below the center of gravity. All right, so first of all we must know that when a body is, say, floating in a liquid, so we have a liquid surface and we have some solid body. All right, so the center of buoyancy lies at the center of volume displaced. All right, so whenever we have a body floating on a liquid, or we have a body submerged in a liquid, and we need to determine the center of gravity, the position of the center of the center of buoyancy. Whenever we need to determine the center of buoyancy, so we should know and learn that the center of buoyancy lies at the center of the displaced fluid. All right, so in this case, this portion, the portion I'm running my pen over, the center of this portion, say, lies here. All right, so the center of buoyancy lies at the center of the volume of the liquid displaced. All right, say we have a submerged body. In this case, the center of the volume displaced is the center of this figure. All right, so this is the center of buoyancy. All right, so the center of buoyancy, let us now check out the options. The center of buoyancy, option A is coincides with the center of gravity. Yes, in some cases it could coincide with the center of gravity, but not always. Say we have a spherical body and it's submerged. In this case, the volume of the fluid displaced and the center of gravity both lie at the center of the sphere. All right, so in this case, the center of gravity and the center of buoyancy both are same and coinciding. All right, but it's not always the case. Say here we have a rectangular body and it's floating. All right, the center of the submerged portion is here and the center of this body, rectangular body, is somewhere here. So these two are not coinciding. All right, so the first option is partially right. However, the second option, which says that it coincides with the centroid of the volume of fluid displaced, this statement is always true. And this is the right answer for this question, that the center of buoyancy always coincides with the center of the volume of fluid displaced. All right, then in some cases it may remain above the center of gravity and in some cases it may remain below the center of gravity. So these are the statements which are true in different cases, but this statement is always true. So option B is the right option for 21. Now let us take a look at the question number 22. So 21 is option B. Now let us take a look at the question number 22. The question number 22 says, if the weight of a body immersed in a fluid exceeds the buoyant force, right, then the body will rise until its weight equals the buoyant force, tend to move downward, and it may finally sink, float, none of the above. All right. So we have a body which is immersed in a fluid, in a static fluid. All right. And let us, for a start, say that this body at this position is in equilibrium. All right. So the weight of the body is equal to the buoyant force at this position. All right. When a force, okay, when the weight of the body, all right, weight of the body, since you know that now that the body is submerged in a fluid, this buoyant force is equal to its weight, that is the weight of the liquid displaced. All right. So when this body is submerged in this liquid, all right, so there is a fixed volume of the liquid that is displaced, say volume V, and there is a fixed weight to that volume, and this weight of that displaced volume is the buoyant force. All right. So the buoyant force is a function of the volume of the fluid displaced. All right. Or we can say that the volume of this body. All right. But the weight of this body is a function of its density. All right. So in a case where the weight of the body is exceeding this buoyant force, weight exceeds the buoyant force, then the body will continue to sink. All right. That is, the body will tend to move downward and it will finally sink. All right. So the option B is the right option for the question number 22. That when the buoyant force is less than the weight of the submerged body, then the body will continue to move downward, because in this case the buoyant force is not enough to support the weight of the body, right? Then definitely the body will tend to move downward and it will ultimately sink. Had the weight of the body been equal to the buoyant force, then there would have been an equilibrium and the body would have stayed afloat. All right. But the weight is exceeding the buoyant force, therefore the buoyant force won't be able to keep the body in a stable position, and hence it will tend to move downward and will ultimately sink. All right. So the option B is the right option for question number 22. Let us take a look at the question number 23. The question number 23 says that the metacentric height for small values of angle of heel is the distance between the center of gravity and the center of buoyancy, center of gravity and metacenter, center of buoyancy and metacenter, free surface and center of buoyancy. All right. So two terms to note down here. First is the angle of heel. All right. So we have seen the angle of heel. Then there is a new term which is the metacentric height. Then we have the metacenter. All right. Then of course the center of gravity, and then the center of buoyancy. All right. So let us take an example. Say we have a body, something like this. All right. So this is a body which is floating on a liquid surface. Then this portion below the surface is the submerged portion, all right? And then the center of this immersed or the submerged portion, which is somewhere here, is the center of buoyancy, all right? Then the center of this rectangle is the center of gravity, all right? So we have a center of buoyancy and this is the center of gravity. Say we have an axis, all right, which is vertical. So this is a vertical axis, all right? So we have a center of buoyancy, a center of gravity, and a vertical axis. Suppose we displace this body by giving a small rotation about this point. Say we give a rotation in this sense, in a clockwise sense, then the vertical axis of this body will have a moment something like this, all right? Say this is the initial position of this vertical axis and this is the position after we give a small rotation to this floating body. Then this angle theta is the angle of heel, all right? So this angle of heel is an angle which the vertical axis makes with its original position or with the vertical on giving a small rotation to this floating body. So this is the angle of heel, all right? So when we have displaced or when we have given a small rotation to this floating body, all right, so this is the position or the initial position of this floating body. And now let us try to interpret the rotated position of this floating body. So when we have given a small rotation to this body, so this is how it would look like, all right? This is the displaced vertical axis and say this is the position of the original vertical axis, all right? This is the angle of heel. Now earlier at the beginning of this rotation, the center of this submerged rectangle was the center of buoyancy. Now that the body has submerged, so the submerged portion is no more a rectangle, all right? So this is the shape of the submerged volume, all right? So the center of the submerged volume is the center of buoyancy, all right? Let us say that the center lies somewhere here, all right? Say this is the position of the center of buoyancy, all right, after this small rotation. But the center of gravity, all right, it will continue to remain at its original position. If it was here before the rotation, all right, it would continue to remain. Say this is the horizontal axis at the beginning, right? So an axis parallel to this, say here, this would be the center of gravity, All right. So this is the center of buoyancy. This is the center of gravity. All right. Now, at this moment, at this position, the weight of this floating body would act along the vertical. Say this is the weight of this floating body W, and at this particular moment this weight will be balanced by the buoyant force. All right, so these two forces will have an opposite sense but an equal magnitude. So this is the net downward force and this is the net upward force at this moment. All right, so we have rotated the body in this direction. All right, so since this rotation is small, all right, and due to this rotation, a restoring moment or a restoring torque would start acting on this body to bring it back to its original position. All right, so in this case, this is the restoring force. All right, so the restoring moment or the restoring couple will be equal to the force times the distance between these two forces. All right, so this is the direction or the line of action of the buoyant force, and this line of action of the buoyant force crosses this vertical axis of the body somewhere at this point. All right, this point is known as the meta center. All right, so this height GM is the metacentric height. All right, so metacentric height is the distance between the center of gravity and metacenter. And what is a metacenter? A metacenter is a point of intersection of the line of action of the buoyant force and the original vertical axis of the body. All right, so let us get back to the question. The question says that the metacentric height for small values of angle of heel is the distance between. So we have to tell what exactly is the metacentric height, and it is the distance of which of the two points in a flotation or a submergence scenario. So the metacentric height is the distance between the center of gravity and the metacenter. All right, so let us get back to the options. So the options are the center of gravity and the center of buoyancy. So a big no. Then a center of gravity and metacenter. Yes, this seems to be the right option. Center of buoyancy and the metacenter, no. Free surface and the center of buoyancy, no. So the metacentric height for small values of angle of heel, or the metacentric height, is the distance between the center of gravity and metacenter. All right, it is generally denoted as GM. G, we can memorize it like this: G is the center of gravity and M is the metacenter, and GM is the metacentric height. So the option B is the right option for the question number 23. All right, so 23 means B. Now, let us take a look at the question number 24. The question number 24 says that a floating body is said to be in a state of stable equilibrium. All right, so we have three types of equilibrium. All right, so we have a stable equilibrium, an unstable equilibrium, and a neutral equilibrium. All right, so if I disturb, say this is the original position of the body, O1. Suppose I disturb this body, it will move to O2 and come back to O1, move to O3 and come back to O1. So when I disturb this body, it has a tendency to move to its original initial position. So this is an example of a stable equilibrium. In an unstable equilibrium, say in a reverse scenario, we have a body and this is the original position of the body, and if I disturb this body in this direction, it will never ever come back to its original position. So if a body has a tendency to move away from its original position, all right, then that is an unstable equilibrium. That means this body is fully disturbed. Then a neutral equilibrium, say if I move a body from its original position on a horizontal plane and then it moves to a new position O2 and stays there. So when we move a body and it stays there, all right, so this is an example of a neutral equilibrium. In an unstable equilibrium, it moves from its original position and does not attain an equilibrium at a new position. All right, and in a stable equilibrium, it has a tendency to move to its original initial position. All right, so a floating body, now we have to draw a correlation between the metacentric height and these types of equilibrium. To understand the correlation between the metacentric height and the types of equilibrium, that is the stable equilibrium, unstable equilibrium, and the neutral equilibrium, let us consider these different scenarios. All right, so the first scenario is, say we have a body, an undisturbed body, which is floating in a liquid. Say the next moment we give a rotation, a small rotation to this body so that it comes to the position 2, which is this position. Now let us try to analyze the various parameters involved in this position. So when I have rotated the body from its original state, all right, and now it is in a rotated stage. Okay, in this rotated state, say the buoyant center or the center of buoyancy has moved from its original position B, all right, to a new position B dash. All right, and the center of gravity would continue to remain as the center of gravity of the body in a rotated state as well. So the position of the center of gravity is unchanged, and since center of buoyancy is the center of volume, the submerged volume was only this volume in this state, And now the submerged volume is a different volume. And since it is a different volume, it has a different center. So here we go. B bar is the new position of the center of buoyancy. So we have the weight of the body acting through the center of gravity, and we have the buoyant force passing through the center of buoyancy. That is the new center of buoyancy, or the center of buoyancy in this rotated state. Now we have to carefully observe the position of the center of buoyancy and the center of gravity. All right, the center of buoyancy has moved to a new position in such a way, all right, that it is generating a restoring couple, because we have a force in this direction and an equal and opposite force in a vertically opposite direction. So we have a couple constituted in an anti-clockwise direction, and the original destabilizing rotation was in a clockwise direction. All right, so we have rotated the body, and its new center of buoyancy has attained such a position that it is generating a restoring couple in this direction, because we have the buoyant force in this direction and the weight of the body in this direction, and both together as a couple are generating a restoring rotation. All right, so in this case, where we have a restoring motion or a restoring rotation, we can further observe that the metacenter, which is the point of intersection of the line of action of the buoyant force and the original vertical axis of the body, that is this point. Let me just use a different darker color. So this is the center of, this is the metacenter, right? And this is the center of gravity. All right, so the metacenter is above the center of gravity. When the metacenter is above the center of gravity, we can say there is a restoring rotation, or the restoring couple. All right, and we have learned just a couple of minutes ago that when we disturb a body and it tends to move to its original initial position, then that is a case of a stable equilibrium. So for a stable equilibrium, we need the metacenter above the center of gravity. Okay, so this metacentric distance, which is GM, is BM minus BG. All right, this is BG. This entire distance is BM. So we have GM, which is positive. All right, GM as a subtraction of BM and BG is positive. All right, so we can say that the distance BM is greater than the distance BG. All right, so when we have BM, that is the distance between the center of buoyancy and the metacenter. When we have this distance greater than the distance between the center of buoyancy and center of gravity, we say that the body is in a stable equilibrium. So different ways to memorize this. We have M above G, we have BM greater than BG, or we have the difference of BM and BG greater than 0. We can say that the body is in a stable equilibrium. All right, now let us move to the third scenario. Suppose we have given a rotation to this body and it has moved in such a way that its position of the center of buoyancy, that is the new position of the center of buoyancy, is in such a way, right, that it is generating a destabilizing couple. All right, in this case, the rotation was generating a restoring couple, and in this case the rotation is generating a couple in the direction of the original rotation, so this body will be destabilized and it will be an unstable equilibrium. It will not move to its original initial position. All right, now let us carefully observe this new position. So we have the center of buoyancy, the new center of buoyancy, as the center of this new submerged volume. All right, so this is the line of action of the center of buoyancy, and this is the line of action of the weight of the body. And at this particular moment, these two forces are equal in magnitude and vertically opposite in direction. All right, so now the line of action of the center of line of action of the bind force is intersecting the original vertical axis of the body at this point. So this point of intersection of the line of action of bind force and the original vertical axis is the metacenter. So in this position, the couple is generated like this. This is the force and this is the force. So we have a clockwise couple, all right, which is exactly in the direction of the original rotation. So we have learned that when we move a body in such a way that it moves away from its original initial position, that situation leads to an unstable equilibrium. All right, so in an unstable equilibrium, we have the metacenter below the center of gravity, or the distance bm, all right, less than the bg. That is, the distance between the center of buoyancy and the metacenter is less than the distance between the center of buoyancy and the center of gravity. All right, so in this scenario, in the previous scenario, the distance between the center of buoyancy and the metacenter was greater than the center of buoyancy and the center of gravity. So we have a reverse scenario here in the case of an unstable equilibrium. We have the distance between the center of buoyancy and the metacenter less than the distance between the center of buoyancy and the center of gravity, which is bm, distance bm is less than bg. All right, so when bm is less than bg, we get a negative or a less than 0 metacentric height. We get a negative metacentric height. All right, so to summarize, m above g stable, m below g unstable. All right, bm greater than bg stable, or in other words, bm less than bg unstable equilibrium. The difference of bn and bg less than 0 is an unstable equilibrium. bm and bg, the difference of bm and bg being greater than 0, or the metacentric height is positive, is a stable equilibrium. Now we have another case. Suppose we have rotated this floating body and it has attained a new position in such a way that its new center of buoyancy is b dash, and the line of action of the bind force is the same line of action of the weight of the body. Or we can say that the line of action of the bind force passes the original vertical axis at the center of gravity. Then in that case, we have this bm distance equal to bg, or the metacentric height is 0 in this case. So in a case where the distance between the metacenter and the center of gravity is 0, then we have a neutral equilibrium. That is, if we rotate the body, this new rotated position would be the new equilibrium position of the body. Right? So to summarize, M above G is stable, metacenter below the center of gravity is unstable, or M below G is unstable, and M coinciding with G is a neutral equilibrium. Now let us go back to the question. The question says a floating body is said to be in a state of stable equilibrium. All right, so stable equilibrium, M above G. So that is when its metacentric height is 0. No, this is a neutral equilibrium. When the metacenter is above the center of gravity. Yes, this should be the answer of this question. The option C is when the metacenter is below the gravity. No, this is an unstable equilibrium. Only when its center of gravity is below its center of buoyancy. That is an altogether different scenario. That is the center of gravity being somewhere below the center of buoyancy. The center of gravity will fall below the center of buoyancy in case of a submerged body. Suppose we have a fully submerged body, right, whose weight is concentrated more towards the bottom or towards the bottom portion. Then we may have a center of gravity here and a center of buoyancy here. All right, since the center of buoyancy is the center of volume. All right, so if the center of buoyancy is above the center of gravity, or the center of gravity is below the center of buoyancy, then this would be the case of a stable equilibrium for a fully submerged body. And similarly, if the center of gravity is above the center of buoyancy, then it would lead to an unstable equilibrium. All right, but this case of the center of buoyancy being above the center of gravity, or the center of buoyancy being below the center of gravity, is valid for a submerged body. We will discuss that in detail in some other question in future. Okay, but relevant to this question is a floating body. So when we talk of a floating body, we talk of a metacenter. And when we don't have a floating body, we only talk in terms of the center of buoyancy and the center of gravity. Right? So this option is ruled out, or it's not applicable to the scenario of a floating body. So the option B is the right answer to this question. Thank you for watching.